Good morning, everybody. Over the weekend, I graded your exams, and I think you got a message from GradeScope saying that your exams were available for you to view. So the class average was an 85, great going. Had a couple of hundreds in there as well. So for most people, the exam went pretty well. So let's keep that up for the next exam and for the final. Great. So this morning I want to continue talking about imines, which is what we were talking about last time. All right, so just to recap, of the imines. The imine results when an aldehyde or a ketone reacts with a primary amine. The reaction is reversible. It happens best under acidic conditions, and the carbon-oxygen double bond of the aldehyde or ketone is replaced by a carbon-nitrogen double bond. That's the imine. And the carbonyl oxygen that was originally present and the two protons that the primary amine comes in with, they end up in a molecule of water. Okay, so that's the net equation for the formation of the imine, and we talked about the mechanism. All right, so I want to continue the thread of the conversation by talking about and recapping what we said last time about some of the reactions of the imine. And one of the most useful reactions of the imine is the reduction of the carbon-nitrogen double bond with hydrogen over a metal catalyst. So we can take hydrogen. We need some kind of metal catalyst, platinum, palladium, nickel, lots of things have been tried. So it's going to be platinum or palladium or nickel. And what happens is the elements of hydrogen add across where the carbon-nitrogen double bond is. So we get the double bond is degraded to a single bond, and the elements of hydrogen add across where that double bond used to be. And so this is a way of making a new amine from a pre-existing amine and an aldehyde or a ketone. Okay, so this is an important reaction of the imine, that reduction of the carbon-nitrogen double bond. Let's talk about the mechanism of this reaction. All right, so mechanism of imine, we can call it reduction, or we can also call it hydrogenation. Okay, so what happens is you have the catalyst surface. So I'm just going to represent this by this little chunk here. This is the catalyst. This is the platinum or the palladium or the nickel. Either any of these will work. And what we do is we dose the catalyst with hydrogen. Hydrogen is a gas, and so we dose the catalyst surface with hydrogen. We just bubble hydrogen across the surface. And what happens is something called a dissociative adsorption, where the hydrogen bond breaks, and now each of these hydrogen atoms are bonded to the catalyst surface. So I'm just going to represent this catalyst in a slightly different way. Right, so that's the platinum or the palladium or the nickel. And what has happened is the hydrogen is now, these two hydrogen atoms used to be bonded together, but now that bond breaks and they become bonded to the surface of the catalyst. On this surface, catalyst surface, you have platinum, palladium, and nickel atoms, and so now the hydrogen is bonded to those atoms. Okay, so this is one way of representing this first step of the mechanism, which is this dissociative adsorption. Let's represent it in another way, in a much more conventional way. We would take hydrogen gas, and expose the catalyst to the hydrogen gas. And what has happened is this hydrogen-hydrogen bond breaks, and now the hydrogen is bonded to the catalyst surface. So that is represented by this symbol here, H dot adsorbed, meaning that this bond here, hydrogen-hydrogen bond, that was 2 electrons. 1 electron goes to 1 hydrogen atom, and the other electron goes to the other hydrogen atom as this bond breaks. So that can be represented by these arrows showing the motion of 1 electron. And so I had 2 hydrogen atoms. Now both of them are adsorbed on the catalyst surface. So this is just a slightly more conventional way of representing this step up here, where we don't have to draw the catalyst and we don't have to draw the hydrogen atom actually landing on the catalyst surface and so on. So we're going to go with this. Okay, so I'm just going to move this up here. H2 gas plus CAT catalyst. You have H dot adsorb plus a second H dot adsorb. And so just to recap, because this is something I don't think we've seen before, is that this hydrogen-hydrogen bond breaks. 1 electron goes to 1 hydrogen atom, the other electron goes to the other hydrogen atom, and they are stuck. They are adsorbed on the catalyst surface. Okay, now it's time for the imine to get involved, because we're talking about the mechanism of imine hydrogenation. The imine is going to represent it this way. Okay, now the imine is the catalyst surface is now dosed with the imine. The imine is either it is exposed in some way to the catalyst surface. Usually the catalyst is little granules. The imine is in solution. And so the granules of catalyst that have hydrogen stuck to them already come into contact with the imine in this way. And a similar sort of thing happens to the imine that happened with the hydrogen. This carbon-nitrogen bond is degraded from a double bond to a single bond, just like the hydrogen-hydrogen bond in hydrogen was degraded to a 0 bond. These hydrogens used to be bonded together, they're not anymore. That represents a drop down of 1 notch from a single bond to no bond at all. Drop down of 1 notch. That's the important concept here. All right, the same thing happens to this carbon-nitrogen double bond, is that this double bond is taken down to a single bond, a drop down of 1 notch from double bond to single bond, and the electrons that form the second bond, one of them goes to the carbon atom, and so that's represented by that dot, and the other one goes to the nitrogen atom. So again, I could represent that with arrows looking like that. One of the bonds in this double bond that got ruptured, 1 electron went to 1 atom and the other electron went to the other atom, and this guy is also adsorbed on the catalyst surface. Okay, so The catalyst has a bunch of stuff stuck onto it, and that stuff is not very happy because nothing has an octet, nothing has an inert gas configuration. It's just being held on the catalyst surface. This carbon here, it only has 7 electrons, right? 2, 4, 6, 7. This nitrogen here, oh, he's in rough shape. He only has 2, 4, 5. Oh, he has an electron there. He has 7 electrons as well. Okay, so these hydrogens, they want to have 2 electrons so that they can be isoelectronic with helium. So nothing here has an octet. Nothing here has a group 8 electron configuration. All of these species, if they weren't stuck to the catalyst, would be extremely reactive. And so now what happens is that the dot from one of these adsorbed hydrogens teams up with the dot of the carbon, the other hydrogen and its dot team up with the dot of the nitrogen, and so now everybody's happy. So you have a hydrogen adsorbed interacts with the carbon atom of the adsorbed imine, and the other hydrogen interacts with its dot, interacts with the dot of the on the nitrogen of the adsorbed imine, and now everybody's happy. So these 2 dots get together, and these 2 dots get together, and so we have the product of the hydrogenation of the imine. The atoms of hydrogen have added across where the double bond used to be. And this thing dissociates from the catalyst surface, and it goes into the solution or into the gas phase or whatever. So this is the mechanism for the hydrogenation. It involves surface adsorbed species where bonds break and then bonds are reformed. Okay, so that's an important reaction of an imine. I'm going to try to do another problem here, but first, bear with me here. Okay, so we're talking about imines. So I wanted to show you some pretty pictures of the imine. All right, so here, here we have a molecule that is used in liquid crystal displays, in TVs, and so on and so forth. And we see this carbon-nitrogen double bond here. We see this carbon-nitrogen double bond here. That's what makes it an imine. And a molecular model of this molecule, the molecule is rod-like. And so this blue represents the nitrogen, the gray is the carbon, the white is the hydrogen. And so this TBBA molecule, which is a commercially important imine, it makes this, it's a rod-like, and it can orient itself based on the voltages that are being supplied by the TV or the cell phone or whatever is using that liquid crystal display. And that's how you get a liquid crystal display. So that's a commercially important imine. All right, so here are some imines from the medical world. Down here, this is Ativan. Here's the imine functionality right here. We see a carbon-nitrogen double bond over here. This is Valium, carbon-nitrogen double bond. These are sedatives and also used as in the treatment of epilepsy. And these are kind of interesting molecules because, like so much other stuff in the medical world, they were discovered completely by accident. Valium was discovered by accident by Leo Sternbach. He was trying to create a liver cancer drug in his laboratory, and the reaction messed up. And, this was like in the 1950s, I guess. It was quite a while ago. And back then, there was not the level of what we would call safety that there is nowadays. You know, you didn't really have to wear safety glasses or work in a hood or anything like that. So he was just working out in the open. The reaction screwed up. He didn't make his liver cancer drug. Instead, what he did was Valium, and he noticed that that at the end of the day, he felt very sedate, very calm, like nothing could bother him. Well, it turned out that the molecule that he had made was this heavy duty sedative Valium. Maybe some of you have heard of its closely related cousin Ativan. This is for anti anxiety. God knows we could all use that now. Okay, we talked about how how a skilled, trained technician can use these strips. This would be in a hospital setting, strips to analyze glucose in the urine of a diabetic, and talked about this chemistry, about how this is glucose, open chain form. This is a primary amine. It's an aldehyde. It's a primary amine. They get together to form an imine, and this imine is blue-green. And so if we look back at this bottle here, this has all of the various colors that you're looking for. And each of these colors on this bottle correlate to a certain level of leukocytes, nitrile, protein, pH, so on and so forth. Okay, another important imine, I think we did a problem with this imine, but I didn't show you this picture, is Mediquox. And this is a poultry aphrodisiac. Who knew, right, that a rooster needed Viagra? Well, that's what this is. You mix this in with its food, and it turns that rooster into the cock of the walk. Another very interesting regime in which we find imine chemistry is the organic chemistry of vision. So you take in dietary carotene, right? You've never seen a rabbit wearing glasses. Here's a bunny, he's wearing sunglasses, but that's just to be cool. Why would you never see a rabbit wearing glasses? Because rabbits eat carrots, and carrots have carotene in them. And the carotene molecule is enzymatically processed into all trans retinol, which is also called vitamin A. Maybe some of you who are interested in dietetics have seen this molecule before. That's vitamin A. And you notice that all of these double bonds in vitamin A are trans. Now there is an oxidation in which this alcohol functionality at the end here is converted to an aldehyde, and then another enzyme gets involved and converts one of these double bonds of this aldehyde to from a trans to a cis double bond, and so we have this 11 cis retinal. Okay, the 11 cis retinal finds its way into the pocket of the enzyme opsin. Where is this happening? This is happening in your eyes. This is happening in your retina. And the enzyme has a lysine residue. This is an amino acid. The amino acid lysine has an NH2 group. The 11 cis retinal is an aldehyde. That's a primary amine. Bang. They get together to form an imine. Okay, and so this is called rhodopsin. So this is, if you're seeing me, if your eyes work, this is happening in your retina right now. And now a photon comes in. A photon comes in and it interacts with this rhodopsin, and it converts the cis double bond back into the trans double bond. But that reaction is accompanied by a huge conformational change in the enzyme. See how this enzyme, I've drawn it so it's kind of has a slipper shape or a kidney shape, something like that, to accommodate this molecule. But when we have the isomerization of the cis to the trans double bond, the enzyme changes shape, and this change of shape, that is relayed to the brain, and that is a nerve impulse that we see as vision. Okay, this imine has done its job. You want to keep watching. You want to keep seeing whatever it is you're seeing. This imine has done its job. We know that imine formation is reversible. So now water finds its way into this enzyme opsin, and it's going to hydrolyze this carbon nitrogen double bond back into a carbonyl carbon and a primary amine, back to an aldehyde. So this last step here, this is just the reversion of the imine to a primary amine and an aldehyde or ketone. And so now here we have the transretinal is generated again, and now it feeds back into this cycle that we showed way up here, this transretinal, and now this happens all over again. And this is how you see. This is the biochemistry of vision. And you can imagine that all of these steps are happening at a huge, huge rate, millions of times per second. The refresh rate of your eyes is extremely fast. It's on the order of microseconds, a millionth of a second. You don't see, it's not like a computer where the screen is illuminated, then it goes blank, and then it and then it's illuminated again, and then it goes blank. Maybe you've seen those lines that across a computer screen when it's filmed with a high-speed camera. That's the refresh rate. Your eyes don't do that, right? Or they do that, but the refresh rate is just unimaginably fast. All of these reactions happening. Okay, so what else do I have here? Okay, I think that's it for now. All right, I want to talk about the biochemistry of nitrogen, but first, let's talk about this molecule here, crystal meth, right? And let's go through how we would make crystal meth. So we can use that hydrogenation of an imine reaction to make this molecule of drug abuse, which is crystal meth. Let's go through some of the steps. We would start off with this ketone. This is called phenylacetone, and we would react that with a primary amine, methylamine acid. All right, it's the recipe for the imine. I see an aldehyde or a ketone. I see an aldehyde or a ketone. I see a primary amine. So these guys are going to get together to make an imine. So we get that. And now we can hydrogenate it with hydrogen over a metal catalyst, hydrogen and some kind of catalyst. I'm going to use nickel, but you could use platinum or palladium. And we talked about how this reaction, the carbon-nitrogen double bond, is knocked down to a carbon-nitrogen single bond, and the atoms of hydrogen add across where that double bond used to be. Okay, so I'm going to draw the structure of this product in a in the conventional way of, yes, there's a hydrogen here that wasn't there before. There's a hydrogen there that wasn't there before, but I'm not going to write it because I like to draw bond line structure. And this is crystal meth. So this would be one way that we could prepare crystal meth in the laboratory. But so don't say you never learned anything practical in this course. But don't try this at home. And it would be very difficult for you to try it at home for a couple of reasons. One reason is this guy here, phenylacetone, and this guy here, methylamine. These are both heavily, heavily watched by the Federal Drug Enforcement Agency, DEA, Drug Enforcement Agency, DEA. Why? Because of reactions like this. Because both of these compounds have legitimate uses, but so much of these compounds is diverted toward illegal drug manufacture that if you try to order these compounds from Chemicals or Us, you have to fill out all kinds of paperwork. You have to be, name, social security number. You have to be screened. You can't have a criminal record, so on and so forth. But this would be one way of creating this crystal meth. This is not how the pros do it. This would be something that you and I would do in the laboratory where we have access to glassware, and we've taken a formal course in working with chemicals in the laboratory setting. Okay, so that's a practical synthesis using the hydrogenation of an imine. All right, now there's another reaction that imines take part in that I want to talk to folks about, and it's not just the imine that does this reaction, it's also other kinds of stuff, and that is tautomerization. This is an important reaction in organic chemistry and also in biochemistry. So first of all, let's just nail down the recipe for tautomerization. Okay, what you're looking for a tautomerizable unit that consists of a double bond, a single bond, and a bond to hydrogen. You're looking for a double bond, a single bond, and a bond to hydrogen. That is the tautomerizable unit. Okay, the reaction is reversible. It happens in either acid or base, H plus and water, or OH minus and water. So the reaction happens both under acidic and basic conditions. And what happens is that the double bond switches places with the single bond. The double bond and the single bond change places, and the hydrogen appears to jump from the single bond end of the tautomerizable unit to what used to be the double bond end of the tautomerizable unit. Up here. Okay, and so this is the product of the tautomerization, and notice that the reaction is reversible because what you're looking for, what things tautomerize, is double, single bond to hydrogen. I have it here, double, single bond to hydrogen. I also have it here in the product, double, single bond to hydrogen, but now it's going the other way. So that's why this tautomerization reaction is reversible, because the starting material and the product, both of them, have this tautomerizable unit. Okay, so that's the overall reaction. Let's do some product prediction and then some mechanisms. Then let's talk about the mechanisms. Okay, the most important tautomerization in organic chemistry is the tautomerization called the ketoenol tautomerization. Okay, this is acetone. Under acidic conditions or basic conditions, acid or base, it undergoes this tautomerization. I see a double, single bond to hydrogen, right? I didn't have to write that hydrogen. I did it now, but since it's a bond line structure, we know that there are hydrogens there without having to write. Okay, so what happens? The double bond and the single bond change places. The double bond and the single bond change places. And the hydrogen jumps from what used to be the single bond end of the tautomerizable unit to what used to be the double bond end of the tautomerizable unit. So there's the tautomer. And again, this can tautomerize back because I see double, single bond to hydrogen. And so this is an equilibrium going back and forth. This is the most important tautomerization in organic chemistry and in biochemistry. It's called the keto-enol tautomerization. Keto doesn't have to be a ketone. This is just what we call this carbon-oxygen double bond. Enol, E means double bond, ol means alcohol. So enol means it's a double bond that has an OH group on it. Okay, so this is the most important tautomerization, but there are others. So let's look at another one. All right, we're talking about imines. So let's look at a tautomerization that would involve an imine. So maybe we have something that looks like this, right? That's the imine. And I see double, single. I'm going to change this to an H. Double, single bond to hydrogen. So this thing can tautomerize as well, acid or base. So this can undergo this tautomerization also, where the double bond and the single bond change places, and the hydrogen appears to jump from one end from what used to be the single bond end to what used to be the double bond end. This tautomerization also has a name. This is the imine. And this guy, this is called the enamine. E means double bond, amine means amine, and enamine is an ene that has an amine on it. Name makes sense. Okay. So now, so you're looking for this double single bond to hydrogen motif. So let's do some problems. I'm not going to have a chance to do this problem from start to finish, so I'll just leave it for you as a for practice. So this molecule here, maybe you recognize this from one of your other courses. This is thymine. This is thymine. It's one of the nitrogenous bases in DNA. So, you know, you've seen with DNA, you've seen that G and that A and that T and that U and so on and so forth. Well, this is the T. Okay, so thymine. Now, before class, I wrote out about 9 tautomers, and I just gave up because that's not all of them. But let's just say, let's try just for fun and practice. How about let's try to write, let's say maybe 3 tautomers of this guy. All right, you're looking for a double, single bond to hydrogen. I see one right here. Double, single, bond to hydrogen. This is a tautomerizable unit up here. I'm going to write TAUT above the arrow showing it's a tautomerization. The double bond and the single bond change places, and the hydrogen jump from one end of the double bond to the other end, from one end of the unit to the other end. So there would be a tautomer. But did you know that tautomers can have tautomers? It's like babies having babies. This guy can turn into this. This guy can revert to the original compound, or this can form a new tautomer of its own, because all you need is that double single bond to hydrogen motif. And I see it right here. Double single bond to hydrogen. So this thing can tautomerize again in a different way, not just reverting to the original compound, but now creating a new molecule where the double bond and the single bond change places, and the hydrogen jumped from one end of the tautomerizable unit to the other end of the tautomerizable unit. Oh, well, this kind of looks like benzene, doesn't it? Right? Because if that nitrogen weren't there, if that were all carbon, it would look like a benzene ring. Okay, so now this guy, let's go back to this one. This one can tautomerize in all kinds of ways, because I see all kinds of double, single bond to hydrogen motifs. So this guy could tautomerize in yet another way. How about maybe double, single bond to hydrogen tautomerization in this direction, which is not a pathway that we have considered up to now. The double bond and the single bond change places, and the hydrogen jumps from one end of the tautomerizable unit to the other. And what I also see here is, double single bond to hydrogen. Here's yet another tautomerizable unit, and this could tautomerize as well. The double bond and the single bond change places. The hydrogen jumps from one end of the double bond, jumps from one end of the tautomerizable unit to the other end. And so here we have yet another tautomer. And all of these species are present in solution, so that when you dissolve this thymine in water solution and add a little pinch of acid or base, it's going to tautomerize to a very complicated mixture of tautomers. It would be nice to know whether you have more of this, or how much of this, or any of this, or how much of it would be nice to be able to quantify this mixture, and we'll see later that there is a way of doing that. Okay, so this was practice in drawing tautomers. Double, single, bond to hydrogen. That's what you're looking for. And you could draw many more tautomers, right? And you don't have to draw the next tautomer from the one you just drew. You can revisit any tautomer and draw more tautomers therefrom. Okay, let's look at mechanism of tautomerization in acid. All right, so I want to demonstrate with the keto-enol tautomer pair. Carbonyl compound, acidic conditions. What's the first thing that nearly always happens? Protonate the carbonyl oxygen. So we would protonate the carbonyl oxygen. And we would have this species. And now, if water is present, and now ordinarily what we would think is that water would come in and attack the carbonyl carbon. Because we said that many times, that when we have a carbonyl compound sitting around in acid, you protonate the carbonyl oxygen and then attack the carbonyl carbon. with a nucleophile. Okay, and so that happens, but that's not tautomerization, right? Tautomerization is going to be now the removal of this proton by some kind of base. It's probably water that comes in here, removes this proton, and we get this motion of electrons. And here is the enol. And the other product of this reaction would be the hydronium ion H3O+. So the mechanism of tautomerization in acid is simply a protonation followed by a deprotonation. You take a proton, you add a proton, and you take a proton away somewhere else in the molecule. We've seen this plenty of times, especially with our acetal mechanism and also with our imine mechanism. Okay, so that's the mechanism in acid. Mechanism in base. Once again, it's going to be just a lot of fiddling and diddling with protons. So here we have the keto form. In basic solution, we have hydroxide, that's a base. Hydroxide picks off this proton in that double single bond to hydrogen unit. These electrons rush in here to make that double bond. We can't stop there, because if we stop there, we'll end up with a carbon with 5 bonds. So I'm going to push this double bond onto that oxygen. So we get water as the product here, and this species here, which is called an enolate. Okay, and so now this water molecule that was produced in the previous step, or another water molecule, comes in, and this is going to function as a proton source. Right, so let me draw the water molecule this way. O- picks off a proton from water. This is an acid-base reaction. The enolate is the base, water is the acid, and there's our enol. And the other product of this reaction would be hydroxide. So the tautomerization mechanisms, it's just fiddling and diddling with protons. You're adding a proton somewhere and taking a proton away. And notice that the reaction is catalyzed by acid or catalyzed by base. So these are fairly simple mechanisms. All right, so we said that it would be very nice. We saw that the keto, we saw that many tautomers can form in solution. And it would be very nice to be able to somehow figure out, well, which tautomer is going to be present in the greater amount. So that's what I want to talk about now. A way of determining whether the keto tautomer or whether the enol tautomer will predominate in solution. Whether the imine tautomer or the enamine tautomer, which will there be more of in solution? And so that's what I want to talk about now. And this is the thermodynamics of tautomerization. We saw that lots and lots of different tautomers can form. Which will be the one that will be present in greater amount? Okay, and so let's draw our two important tautomers. I'm drawing the keto tautomer, and that's in equilibrium with the enol tautomer. Right, that's the enol tautomer, and it would be nice to know, well, in solution, do I have more keto tautomer, do I have more enol tautomer? One way is to determine look at the thermodynamics of this reaction. What were the bonds that were broken going from the ketotautomer to the enoltautomer? Well, the carbon-oxygen double bond was broken. I see a carbon-oxygen double bond here. I don't see one here. So that was broken. What other bond was broken? The carbon-carbon single bond was broken. I see a carbon-carbon single bond here. I don't see a carbon-carbon single bond here. I see a carbon-carbon double bond. So the carbon-carbon single bond went away. What else was broken here? The carbon-hydrogen bond was broken. I see a carbon-hydrogen bond here. I don't see a carbon-hydrogen bond over there. Okay, now let's look at this guy over here, and let's talk about what were the bonds that were formed. Well, over here, I see a carbon-carbon double bond in the product that did not exist in the starting material. So the carbon-carbon double bond was formed. What other bond was formed? Oh, a carbon-oxygen single bond was formed. I see a carbon-oxygen single bond here. I don't see a carbon-oxygen single bond here. I see a carbon-carbon double bond. What else happened? Well, I also formed an oxygen-hydrogen single bond. And once again, I see an oxygen-hydrogen single bond here. I don't see one here. So those were the bonds that were formed, and those were the bonds that were broken. Okay, and now what I do is I jump on the internet or go to the library and look up the bond strengths of each of these bonds. Okay, the carbon-oxygen double bond, that is worth 754. This is kilojoule per mole. The carbon-carbon single bond, that was worth 332 kilojoules per mole, and the carbon-hydrogen single bond, that's worth 414 kilojoules per mole. Where am I coming up with these numbers? I looked them up. Do you have to memorize these numbers? No. You have to be able to do a calculation like this? Yes. The carbon-carbon double bond is 611. Carbon-oxygen single bond is 344. And the oxygen-hydrogen single bond is 346. Okay, so this is what all of these bonds are worth. Okay, total, the sum of the bonds that were broken, this works out to, I got 1,500 kilojoules per mole. This is all kilojoules per mole. The sum of the bonds that were formed, I got 1,420 kilojoules per mole. Okay, so now I'm ready to come up with the big payoff. So maybe you remember delta H from Gen Chem, right? This is the amount of heat that, this is enthalpy, this is the amount of heat in or out of the system at constant pressure. And most of the chemical reactions that we're interested in, every kind of biological reaction, for example, happens under constant pressure, not constant volume. So the overall change in enthalpy, this is equal to the sum of the bonds, broken minus the sum of the bonds formed. Right, and when you do the math here, 1,500, this comes in as a positive number, minus the bonds formed, 1,420. So I get delta H here is plus 80 kilojoules per mole. Okay, and so this is saying that this transformation here is uphill, right? If I start here and break all of these bonds and then put all of these bonds back together, I am going up 80 kilojoules per mole. So this this number here, this positive number here, is telling me that the reactant is more stable, right? Because I just calculated to go from this reactant to this product, I'm going uphill by 80 kilojoules. I have to put energy into the system. It's not going to go through this reaction all by itself. It has to get energy from its surroundings, 80 kilojoules per mole. So my big payoff here is that the keto form is 80 kilojoules per mole more stable than the enol form. So in the equilibrium mixture, this guy predominates. This guy is the dominant form. So that I'm going to have more of this than of this at equilibrium, as demonstrated by this calculation. Okay, so just to recap, I'm looking for all the bonds that were broken. I have numbers for all of them. I'm looking for all the bonds that were formed. I have numbers for all of them. The delta H, the change in enthalpy, the change in heat, is the sum of the bonds that were broken minus the bonds that were formed. Okay, so now you try it. We talked about the imine-enamine tautomer pair. So there's the imine, double, single, bond to hydrogen, do all of that jazz that we've been talking about. Grab that. Okay, and so now the data, this carbon nitrogen double bond, this is worth 588. That got broken. This carbon-carbon single bond, that got broken. I don't see a carbon-carbon single bond in the tautomer. He was worth 332. This carbon-hydrogen bond, he got broken. I don't see a carbon-hydrogen bond in the product. He's worth 414. Over here, this is a new bond, right? I didn't have a carbon-nitrogen single bond in the reactant. I had a carbon-nitrogen double bond. So he's new. He's worth 344. This carbon-carbon double bond, he's new. He's worth 611. And this nitrogen-hydrogen bond, he's new. He was worth 372. Okay, so now I would like for you to get out your calculator and tell me what is the delta H of this transformation. Sum the bonds formed, sum the bonds broken. The delta H is going to be bonds broken minus bonds formed. Right, this is the imine, and this is the enamine. They're tautomeric pairs. Which one is dominant? So it's a good chance, good place for you to have a workout with your calculator, right? Anyone come up with the answer? Anybody up there have the answer? Anybody trying the problem out? I got plus 7 kilojoule per mole. Okay, so that's bonds broken minus bonds formed, plus 7. So who's more stable, the imine or the enamine? How do we interpret this number? We know how to calculate it, but how do we interpret it? Who's more stable, the imine or the enamine? In the equilibrium mixture, which one is going to be dominant? Well, this is a positive number. That means in going from the reactant to the product, you're going up 7 kilojoules per mole. Put that on an energy diagram. Here's the imine. Here's the enamine. Right, this is H, standard. Yeah, who's more stable? The imine is. The imine is lower by 7 kilojoules per mole. Right, so in the equilibrium mixture, you're going to have more imine than you will have enamine. This one is dominant. Okay, well, that's all I have for you today. So do check out your exams on GradeScope. Any questions about anything before we quit? No? Okay. See you next time. Bye-bye.